When we left off, we were searching through the pKa table for a weak acid that might be good as a buffering range for the blood at pH 7.4. And we said that perhaps it would be the pKa of 7.2 for phosphate, monobasic, whatever that is, that would do the trick. Well, let's go on to the next page and do a titration that will help us find out whether that's the case or not. So here we are going to do the titration of what we call a polyprotic acid. That is a weak acid that has more than one proton. Now, we mentioned before that we were interested in monobasic phosphate and its pKa of 7.2. But it turns out monobasic phosphate is actually both a base and an acid, and it's part of a series of titration from phosphoric acid. Now, let's consider that if we start with weak acid phosphoric acid, let's call that species A, it has 3 protons, and those protons are all equivalent. Now, the first proton to come off, however, if we just peek back here, is from phosphoric acid, and phosphoric acid has a pKa of 2.14. That's a much stronger acid, and we can define the loss of that proton by putting the 2.14 pKa above that arrow there, telling us what it means to go from triply protonated phosphoric acid to monobasic. Now, what is monobasic? That's where we have 2 protons left, but we've removed a proton and replaced it with a salt of sodium. So if we were to challenge phosphoric acid with sodium phosphate, we would end up with 1 proton removed, and we would get a second species called monobasic phosphate. Now, monobasic phosphate is a base, but it's also an acid, and the proton for the next one to come off is pKa of 7.2. That's the one we were interested in. And if we were to do that, we would get species C in this series, and that would be 2 negative charges and a proton. I'm going to skip the sodiums on there, but they would be there. It would be 2 NAs associated, one each with one of those negative charges. If we were to deprotonate again, we would get tribasic with 3 sodiums on there, and that would be species D. So this is a bit more complex than what we saw before. Let's go back to the previous page and look at dibasic phosphate, which is right here. That has a pKa of 12.4. Let's finish off this chart by coming back and adding that right here. Okay, so monobasic phosphate that we're interested in is part of a series of phosphate molecules derived from phosphoric acid. What would a titration of phosphoric acid look like? Well, it's a triprotic acid, and if we put it in a water solution and measured the pH, it would be pretty low, down in between 1 and 2 perhaps. Now, if there's 3 protons, that means we need more than 1 hydroxide ion to interact one with each of those protons on there. So if we're going to put the number of equivalents that we need down here, it wouldn't be 1 equivalent. We would need 1, 2, 3 total equivalents to interact with that phosphoric acid and bring it all the way from phosphoric acid here all the way over to tribasic phosphate. And that's what our goal is, to go all the way from the beginning all the way to the end. So we're going to need 3 equivalents. Notice I divvied up this chart in 3 perfectly equal segments. They're equivalents after all. Now, let's go to the titration. This is how it's going to work. I am going to start with a fully protonated phosphoric acid way down here in the corner, and that first equivalent is going to carry us from A to B. This is how it works. Notice that the conversion of phosphoric acid to monobasic phosphate is governed by a pKa of 2.14. We know that right in the middle of that equivalent is the point where the pKa is equal to the pH. So I'm going to start there, not all the way on the left, but I'm going to start right at the 50% mark of the first equivalent. I'm going to make a dot there for the pKa. I'm going to draw a roughly straight line through that covers about 90% of the equivalents. On the left, I'm going to kind of make a concave curve down, and on the right, I'm going to make a concave curve up. And at that point, we have completed our first equivalency. Okay, good. That gets us to letter B. Let's not write that down quite yet, but I want to go from letter B now. Monobasic phosphate is going to now be our acid, and we're going to titrate to dibasic phosphate and remove another proton. That's governed by a pKa of 7.2. So once again, we're going to go, and at 7.2, we're going to put it right at the point where midpoint through 1 to 2, the second equivalent. We're going to draw a nice gentle slope going through that, over 90% of it. We're going to concave curve down on the on the left, concave up on the right, and now we've completed that equivalency. What about the last one, from C to D? That's governed by a pKa of 12.74. We're going to do the same thing. At the midpoint of the third titration, we're going to put a line straight through that 12.74, concave down on the left, concave up on the right, and at this point we have what looks to be like 3 unique titrations, but they're not. In fact, what we're going to do is go back and fill in these gaps because this is all one titration curve. Let's start on the left and go through this again. We start with 100% phosphoric acid. That's how you always start titrations, is a fully protonated form. We're going to go through one equivalent, and right here we are now going to have about as much of letter B, monobasic, as we can. Then we go through the second titration to here, at that point there, we have almost 100% C, and then we go through the last titration. At the very end, you have about 100% D. Okay, this finishes our titration of acetic acid. At least we've got the curve. I'm going to stop the video here, and we're going to pick up the same titration curve on the next page to see if this is going to serve as a good buffer for blood.